Hello everyone, and welcome to this video in which I'll be introducing you to limits and some basic limit laws. So the way this video will be structured is we'll start with some theory, what limits are, some basic laws, and then after that we will do a few examples and check comprehension. So if you're just here looking to maybe do some practice problems along with me, then feel free to skip ahead to that section of the video. So in order to be able to understand limits, let's first remind ourselves how functions work. So given a function f of x, f of a denotes the output for input x equals a. So the output would be the function of a value, and the input is a value for x, in this case some arbitrary parameter a. And limits are very similar to this, except that they are useful for assigning function values or f values for input, meaning a values, for which the function isn't defined. And the way that limits are evaluated are by looking at the y values or function values of the function at x coordinates close to that a value that we're interested in. So limits are written in this format shown over here. So the LIM stands for, it's short for limit, and then underneath we write the variable tends to some constant. So in this case, the variable is x and the constant is a, but which constant the variable tends to, in this case the constant is some a, but this constant is usually given in the question. So for example, x could tend to 5 or to 3, any constant really, and sometimes it can also tend to infinity and negative infinity. Meanwhile, x isn't just substituted by some constant, x is the variable. And then over here, we just have some function of x. So this function could, for example, be f of x equals x squared, or f of x equals 5x plus 3. Really, it can just be any function. And this is read as the limit as x tends to a, or as x approaches a, of f of x. Now, originally we said that limits are often used in order to assign function values for, or output values for input values x, for which the function isn't defined. But it's also possible to evaluate a limit of a function as x tends to some value a, even if the function f of a is defined at a, even if the function f of x is defined at a. And in that case, if the function f of x is defined at a and x tends to a, then intuitively the limit as x tends to a of f of x is just equal to f of a, or the function evaluated at a. And keep in mind, this is only true in the cases where the function exists and is defined at x equals a. So an example of this would be the limit as x tends to 5 of the function x plus 10. So here we can just replace this. We can just directly substitute this by the function of 5, because x is tending to 5, and this is equal to 5 plus 10, because x is 5, and that's just 15. So one way of evaluating a limit is simply replacing x by that a value and evaluating function of a. And again, this only works if f of a is defined, or f of x is defined at x equals a. So this method is just called direct substitution because we're just substituting x by a. So if we look at this graph where y is just some function of x, y equals f of x, we notice that y is defined over many x values. It's defined over here, it's defined over here, it's defined over here. But there is one hole where y is not defined, specifically here. So this hole means that at this x value, whichever it is, over here, the function isn't defined. There's no corresponding y value. So in this case, we wouldn't simply be able to replace f of x by that x value that corresponds to this hole, because the function isn't defined at that point. But the limit as x tends to this x value of f of x is defined, because we can see the y value just, or the y values just below that x value and just above that x value, so we can tell what y should be at that point by looking at the outputs as the x inputs tend to this x value. Now, there are multiple methods for evaluating limits, and sometimes we need to combine two or more of these methods in order to successfully evaluate a limit. So the most basic one that we already covered is direct substitution. That is this method, but of course the function has to be defined at that point. Now, direct substitution can also be applied after some other steps. Some other methods have been applied on a limit, so after we've rewritten it in some other form, maybe then after it's been rewritten, we can use direct substitution to solve the limit. The second method would be simplifications, and that would consist of algebraically manipulating the function that we're evaluating the limit of in such a way that we're allowed to do, and also that leads to a different form of the function, in which we are allowed to just use direct substitution. So doing some manipulation before applying direct substitution. Now, some of these manipulations consists of applying limit laws, which we're about to see now, or rather in a bit. And then there are also further techniques, such as using the fact that the limit of sine x over x as x tends to 0 is equal to 1, as well as L'Hopital's rule, but those won't be covered in this video, as this is just a basic introductory video. They could be covered in another video. Let us know in the comments whether you'd be interested in a video like that. But for now, we will just be focusing on these three methods for now in this video. So it's also important to note that not all limits exist. And there's actually a condition for existence, a test that can be applied to check whether a certain limit exists. And if you're ever asked to solve an exercise and the limit doesn't exist, what you're supposed to do is just write DNE for does not exist, and of course show that it doesn't exist or explain why it doesn't exist. So this test for existence is the following. So the limit as x tends to a of f of x exists only if it is equal to the limit as x tends to a plus of f of x, and that is also equal to the limit as x tends to a minus of f of x. Now, x tending to a plus or a minus well, for example, x tending to a plus would be looking at y values as x tends to a, but from the for values slightly bigger than a. So that would mean as x approaches a from the right side. And then for x tending to a minus, it would be for x values as they approach some a value from the left, so for slightly smaller x values. And then if those are equal, if those two limits are equal, then our main limit exists. Now, on a graph, x tending to a plus would be this region over here, so slightly to the right of our point of interest, and then x tending to a minus would be this region here, and that would be slightly to the left of our point of interest. So the first three laws that we will be looking at are the following. So they deal with sort of splitting the limit as x tends to some value a of two functions of x related in some different ways. So in the first law, we look at how we can actually separate this limit. So if we have the limit as x tends to some value a of one function of x plus or minus another function of x, then we're allowed to just rewrite this as the limit as x tends to a of one of the functions plus or minus, depending on whether we had plus or minus in the original form, plus or minus the limit as x tends to a of the second function, or in this case, g of x. So we are allowed to just sort of split the limit as long as we have the same thing over here, x tending to the same value, or in this case, the arbitrary a, and of course, f of x has to be the same as f of x over here, and then g of x has to be the same as g of x here. And if we started with a plus, we're going to have a plus here as well. If we started with a minus, we're going to have a minus here as well. And then something similar applies to the limit of functions that are multiplied together. So we still have x tending to the same value on both the left side and the right side. But yeah, we are allowed to split the limit of the product of two functions into the limit as x tends to a of one of the functions multiplied by the limit as x tends to a of the other function, g of x. And the same applies to division or fractions. The limit as x tends to a of f of x over g of x is equal to the limit as x tends to a of f of x over the limit as x tends to a of g of x. Of course, given that g of x, given that the limit as x tends to a of g of x is not zero, of course we can't have 0 in our denominator. Okay, so now let's do some exercises to apply what we've learned. So, in the first exercise, we have to evaluate the limit as x tends to 2 of the function 5x plus 3. So, in this case, if we just substitute x by 2, we get a sensible result. So, we're allowed to just do that because this function is defined at x equals 2. So, we would have 5 times 2 plus 3, which is 10 plus 3, or 13. Okay, the next one. The limit as x tends to 0 of the square root of x. The first thing we test for is whether we can immediately just substitute. And when we substitute, we don't get any illogical result, such as division by 0, for example. We just get the square root of 0, which we do know the value of, and this is just 0. And that's our answer. Then, the limit as x tends to 0 of this fraction. So, you might notice that if we just substitute x by 0 everywhere, we're going to have 2 times 0 in the denominator. So that's a denominator of 0. And that cannot be done because division by 0 isn't defined. So this function has a discontinuity at x equals 0 and is not defined at x equals 0. So we have to manipulate this fraction in a way to try to eliminate this denominator of 0. And one way how we can do that is to just factor out an x on the numerator. So we have x squared plus 5x, and after factoring out an x, we will have left in the brackets x plus 5. If you were to expand this, you would find the original x squared plus 5x. And then on the denominator, we still have 2x. So now we can actually just cancel out the x's on the numerator and the denominator. We're essentially dividing the numerator by x, and we're dividing the denominator by x. So then after that operation, we're just left with x plus 5 over 2. And now when x tends to 0, we're just going to have 5 on the numerator and 2 on the denominator. So that's our final answer, 5 over 2. Then number 4, the limit as x tends to 0 of x over x. So again, we have this issue if we directly just substitute x by 0, we have this what's called an indeterminate form. We would have 0 over 0. But what we can do actually is just simplify these x's. So we're left with the limit as x tends to 0 of 1 over 1, right? Or just 1. And now if this function is independent of x, so if we just have a constant here, such as 1, which we do in this case, then that's just our answer. Our final answer is 1. So if we have a limit as some variable tends to some constant c of a constant, then the answer to that is just the constant we have over here. Okay, number 5, the limit as x tends to 0 of 1 over x. So again, we have this problem where if we were to just substitute x by 0, we would have 1 over 0, which is not defined. So this fraction seems in a pretty simple form. So it doesn't look like there's anything that can be done to it. So in this case, why don't we just think about what happens to 1 over x as x tends to 0. So let's look at it from the positive side and from the negative side. So if these are our axes, then on the positive side we would have something like this, a rectangular hyperbola. So as x tends to 0 from the positive side, we would be getting closer and closer to positive infinity, rather. But on the negative x-axis, on the negative part of the x-axis, as x tends to 0 from the negative side, we're actually approaching negative infinity. So we have this vertical asymptote at x equals to 0. So this means that the limit as x tends to 0 plus, that is from the positive side of 1 over x, that is infinity, right? However, the limit as x tends to 0 minus of 1 over x, so from the negative side, that is negative infinity. And positive infinity is not equal to negative infinity. So this limit, as x tends to 0 of 1 over x, is not defined. So we just say it does not exist. Because the limit as x tends to 0 plus of that function and as it tends to 0 minus of that function, they do not converge to the same value. One converges to infinity over here, and the other just goes to negative infinity. So the overall limit doesn't exist. And for the next one, we have the limit as k tends to infinity of 1 over k. Here we can just try directly substituting, and usually we do that with a pencil in quotation marks. So we would have 1 over infinity, And as if we have 1 and divided by a very, very, very large positive number that tends to infinity, well, we will just be approaching 0. So since we're calculating the limit, this is just 0. So whenever you get 1 over infinity from a limit, you can just say that's equal to 0. And if it were 1 over negative infinity, then that would also be 0. But it would approach 0 from the negative side, and here we're approaching 0 from the positive side. But yeah, 0 plus and 0 minus are both still just 0. Okay, let's move on to the next one. So we have the limit as x tends to infinity of the natural logarithm of x. So if we try direct substitution, what we would get is ln of infinity. And this is just infinity because, well, if we start with some number and we take the ln of it, we're going to get a smaller number. But as our original number becomes bigger and bigger and bigger and closer to infinity, even the natural logarithm of that number will still just grow indefinitely to infinity. And the same logic applies to the next limit, which is the limit as x tends to infinity of the square root of x. So although the square root square root of infinity in quotation marks. So although the square root decreases our x value, as x tends to infinity, our function square root of x is still going to grow forever to infinity. It doesn't converge to a single real value. So our final answer for this limit is also just positive infinity. Okay, so we have the limit as n tends to infinity of k to the power of 1 over n. It isn't specified here, but k is just some constant. Doesn't matter which one it is, because yeah, no matter whether it's 2 or 3 or 4 or so on, the limit is just going to converge to the same value for any constant k. So what we can do is, after copying our limit as n tends to infinity, what we can do is just think about what happens to 1 over n as n tends to infinity. And we actually already had a similar example here. Well, this 1 over n just tends to 0. So we can replace this by k to the power of 0 instead of k to the power of 1 over n, because the power is just going to grow closer and closer to 0. Now we know that any number to the power of 0 is just 1. So in the end we have the limit as n tends to infinity of 1. And again we have the limit of a constant, and we know that this is just our constant, so 1 in our case, and that's our final answer. Now, of course, 0 to the power of 0 is undefined, so k would go in our case. Okay, let's move on to the next one. We have the limit as theta tends to 0 of sine of x. So if we imagine our unit circle, okay, or the graph of sine of x, you would know that as theta tends to 0 of sine theta would just be 0. And that's the case for theta approaching 0 from the left side and from the right side. And of course here to be sine theta, actually, not sine of x. And same for the next one. So we have the limit as theta tends to pi over 2 plus of tangent theta. So we have, it's been specified that we're approaching pi over 2 from the right side. So if we were to draw the graph of tangent of theta, it would look something like this, okay, where we have asymptotes. And one of these asymptotes is at pi over 2, okay, but we're approaching it from the right side, so that would be in this area here, and we can see that the graph just tends to minus infinity. So sometimes it's useful to think of the graph and maybe sketch it in order to help you evaluate limits. Okay, so we have the limit as x tends to negative infinity of k to the power of x. Okay, so again, k is just some constant. Now, if x is tending to negative infinity, that's the equivalent of rewriting this as the limit as x tends to positive infinity of 1 over k to the x. So we've gotten rid of the negative sign, but to cancel that out, we've taken the inverse, because a negative sign in the exponent, like we used to have, has the effect of taking the inverse. Okay, so here, if we have just some constant raised to a really big power that is tending to infinity, this is just bringing the denominator closer and closer to infinity, and 1 over infinity would just be 0. So that's our final answer. Then number 13, the limit as x tends to infinity of 3x plus 2 over 5x plus 7. So this function is known as a rectangular hyperbola, and this limit would be really easy to solve with L'Hopital's rule. But for now, since we haven't seen it yet, the way we would bring reasoning into solving this limit would be the following. So we have a linear function on the numerator and a linear function on the denominator, and if we were to just substitute x by infinity, we would be getting infinity over infinity, which is an indeterminate form. It could have lots of different values, but in this specific case, right, we have to focus on the 3x over 5x, because as both the numerator and the denominator tend to infinity, these plus constants aren't going to have any effect compared to the large x values that are the main cause for growth. So we can just say this is equal to the limit as x tends to infinity of 3x over 5x. And of course this is only true in the limit, as x is tending to infinity. If we didn't have these limits, this step obviously wouldn't be allowed. But since we're working with limits and x is tending to infinity, we're allowed to do that, and we'll see in a later video why we can do that when we learn about L'Hopital's rule. But now that we're here, we can, of course, cancel out these x's, and we get 3 over 5, which is a constant, so we can just bring it out of the limit. So 3 over 5 is our final answer. Okay, next one, we have the limit as x tends to 3 of x squared minus 9 over x minus 3. So again, if we were to just substitute x by 3, we would get 0 on the denominator. So we have to transform our function in some way, but keeping it equal to the original function, of course, just rewriting it in some way. So why don't we try factorizing the numerator? We have x squared minus 9, so we can use the difference of two squares factorization method. So 9 is just 3 squared, so we have x squared minus 3 squared, and this is equal to x plus 3 times x minus 3. With brackets like so, and then we still have x minus 3 on the denominator, and we can put brackets around it as well. And now we see that the x minus 3 bracket nicely cancels out, and we're just left with x plus 3. So this is what we have remaining, and x is tending to 3. So if we have x plus 3 and x is tending to 3, that's just going to be 6. So here, after we've factorized and cancelled out, we can just use direct substitution to get 6 as a final answer. And actually, here, of course, we should still have our limit in this step. So the limit is x tends to 3. Okay, let's do one which is a little bit longer. So the trick for this limit, we have x tending to infinity of the square root of x squared plus x minus x. The trick is to multiply by what we call a perfect 1. So you know that we're allowed to just multiply this by 1, right? But that wouldn't help us very much. So why don't we multiply it by a fraction of the form k over k? Because this is just 1, right? So we're allowed to do that. And what should our k be? Well, we want some things to cancel out. So let's try the square root of x squared plus x. And now we're going to have plus x. So notice how this is very similar to this, but instead of minus x, we have plus x, because we want to use the difference of two squares formula in order to get our limit in a better form. So of course we also have to have the same thing on the denominator, x squared plus x, and then plus x outside of the square root. So we're allowed to multiply by this because that's just 1. So now let's multiply this with this numerator, and then we're still going to have this on the denominator. So for this multiplication, we have the factorization of a difference of two squares, okay, where this is the a number and this is the b number. So we can actually rewrite this as the limit as x tends to infinity of this square, which is just x squared plus x, right? Because our square will cancel out with the square root. And then we have minus our x squared, okay? And then on the denominator, we still have this, this left over. So we'll just copy that as it is. X squared plus x, and then plus x outside the square root. So we're just copying the denominator, and if you're not sure how we got to this numerator, you can try factorizing this, and you'll see that you'll get this product as a result, using the difference of two squares formula. Okay, so now that we got into here, we notice that we can cancel out plus x squared and minus x squared. So on the numerator, we're just left with positive x. So let's write that down. We have the limit as x tends to infinity of x over something. Now, we have on the denominator a square root of x squared plus x, right? So let's factor out an x squared from this expression, still under the square root. So inside the brackets, we're going to have 1 plus 1 over x, right? All under the square root, because if we were to distribute this x squared to both terms, we would find back what we originally had. So we're allowed to do that, and then let's bring this x squared outside of the square root. So it's just going to become an x, because when an x squared leaves a square root, it just becomes x. And then under the square root, we still have the 1 plus 1 over x, okay? So I'm going to write that over here, x times the square root of 1 plus 1 over x. And then outside of the square root, we still have this plus x over here. So I'm going to delete this now. Okay, and now we can simplify the x's. So get rid of this x, get rid of this x, and of course of this x. We have to divide the whole denominator by x. So we divide this term by x, but also this term by x. So then what we have left over is the limit as x tends to infinity of 1, because when we divide by x, we're left over with 1 over here, over the square root of 1 plus 1 over x plus the 1, since we're dividing by x, so we have another 1 left over. Okay, now let's evaluate the limit. As x tends to infinity, this term just approaches 0, because 1 over a very big number is just a number very close to 0, and in the limit, it just becomes 0. So we have the square root of 1 plus 0, and that's just 1. So we have 1 over the square root of 1 plus 1, and that's just 1/2. And that's our final answer for this limit. Okay, let's do one last one. We have the limit as h tends to 0 of x plus h squared minus x squared all over h. So why don't we use the difference of two squares formula to factorize this, and then hopefully something will cancel out conveniently. So we're going to have the limit as h tends to 0 of x plus h minus x times x plus h plus x all over h. So this is just applying the difference of two squares formula. If you're not convinced, you could try expanding this and you'll find this result back. So we know they're equal, and now we see x's canceling out. So let's rewrite this as the limit as h tends to 0. And I forgot to mention this, but of course we can't use direct substitution because we'd have 0 in the denominator. So the limit as h tends to 0 of h, because that's all that's left over from this bracket, h times, and in this one we have 2x plus h. So 2x plus h, and then all over h. So we can cancel the h's out, and we find that this is equal to the limit as h tends to 0 of 2x plus h. And now that we've reduced the limit to this form, we can just substitute h by 0, because we just have plus 0, and that's absolutely fine. So this tells us that the final answer is just 2x, because plus 0 doesn't have any effect. So 2x is our final answer. Yeah, that's the end of the video. Thank you guys for watching, and we'll probably make another one on limits part 2, to discuss some further techniques for evaluating limits, such as L'Hopital's rule, the trigonometric limit sine x over x as x is tending to 0, stuff like that. Just go further into detail, and of course we'll also do exercises with those. So yeah, let us know in the comments if you'd be interested in that, and I look forward to making another video.